Yeah, hi there. In this tutorial, we are going to cover NumExpr library of Python. Basically, this library helps to make you run code faster, especially if it involves some mathematical calculations. So one interesting way of achieving parallelism in Python is through NumExpr library, so in which a symbolic evaluator transforms Python expression into high performance vectorized code. So how NumExpr achieves the faster response is by vectorizing in chunks of elements instead of compiling everything at once. So that's the underlying principle. So if you have not installed it, you can install it using pip install numexpr. Once it is done, once the installation is done of this library, you can import it like this: import numexpr as any. The version I am using is 2.7.1. So just to quick overview again, so NumExpr is a fast numerical expression evaluator of NumPy. So with it, expressions that operate on arrays are accelerated and they use less memory than doing the same calculation in the native Python. So it is a multi-threaded capabilities. It can make use of all the cores. So how NumExpr works better? The main reason why NumExpr achieves better performance than NumPy is that it avoids allocating memory for intermediate results. So due to this, it results in better cache utilization and reduces memory access. So what I am going to do now, I am going to import couple of libraries like NumPy, Pandas, and Matplotlib, and I'll start with the simple vector expressions. So first is A and B. I'm creating two vectors with 1 million data points in each of these. And the simple one expression is I'm just subtracting 10a minus 5b and I'm timing it. So it took around 20.4 milliseconds in the normal Pythonic way. Now, if I do the same thing using any dot evaluate, so the way to give your any expression using this package is like this. You say ne, which is the alias that we have specified above. If you see num expr as any, so any is that, and then we have to specify dot evaluate method, and within that we have to specify our expression in the double quotes or single quotes. So the way to give it is any dot evaluate and within bracket put your expression in quotes. So if I run the same thing 10a minus 5b, so where each a and b containing 1 million data points, then it took around 5.58 milliseconds. So you can see from 20.20 milliseconds it came down to around 5 milliseconds. Considerable improvement. Now let's take another example where what we are doing is I'm creating four arrays x1, x2, y1, y2, and each of these having 1 million data points. So basically what I'll do is I'll calculate the distance between the 2 points. So x1, y1 and x1, x2, y2 are are 2 points. So as you know, the distance between the 2 points is x1 minus x2 square plus y1 minus y2 square to the whole square root. So that's how to calculate the distance between the 2 points. So this is the same thing I am going to do it here. So if I do it in a normal Python way, okay, just by specifying the NumPy library, and if we calculate the difference between the data points or difference between the points, and then I am putting an additional condition that if the distance is greater than zero point 0.5 or not, I'm just putting a check on it. So it will give the output in the form of true or false. That is, it will calculate the distance between the 2 points, and then it will see whether this distance is greater than zero point 0.5 or not. If it is greater, then it will return true, otherwise false. So that is the Boolean filtering that we are doing. Now, if I run this, it took around 38.1 milliseconds, whereas the same expression, if I do it using any.evaluate, and it took around 7.5 milliseconds, again from 38 milliseconds to roughly around 8 milliseconds. Another example I'm taking is I'm just taking I'm creating three large vectors A, B, C, each of which having 1 million data points. Now I'm putting some large calculations where it's like b square plus ca plus 1 into 3 and adding all this to the vector A. So it took around 34.9, around 35 milliseconds with normal Python. But if I do the same expression using any.evaluate, then it takes around 6.8 milliseconds. So we have performed three different calculations, one with the three large vector calculations giving a large expression, another is applying the Boolean filtering, and the first one was the simple vector expression. So in each of these examples, we've seen that the time has improved uh, by at least 5 times to 6 times when we are using any.evaluate compared to when we are just simply uh, calculating the expression. Okay, so next is this package also allows you to specify the number of cores. So the way to specify the number of cores is by using the function set num threads. So in that you can pass the number of threads to be used. So what I've done here is I'm just creating a loop which starts from 0 to 4, 0 to 3 actually, as 4 is mm, as it's a range, so it will start from 0 and go up to 3. So I'm setting it the number of threads using any dot set num threads and then evaluating the expression. And then we found that as the number of cores increase, the time it took was less. It goes down from 10.6 to 8.2 to 7.23. So in this way, if we have some large calculations to be done, especially large numerical calculations to be done in our analysis, then it is better to make the use of this package NumExpr, so that drastically improves the performance in terms of the time, and it also allows you to give the option of specifying the number of processors, that is number of cores, so we can achieve parallelism also using this package. So that's it for now in this tutorial. Thank you.